In the quiet hum of server farms, a profound mystery has taken root within the architecture of modern computing. Researchers training massive neural networks to simply predict the next word in a sequence began noticing anomalies. The systems were successfully translating between languages they were never explicitly taught, passing professional licensing exams, and writing functional computer code. These machines were not programmed to perform these specific tasks. They were simply fed vast amounts of text and given immense computational power. This phenomenon is known in the field as emergent capabilities. In complex systems, emergence occurs when a system develops properties that its individual parts do not possess on their own. For artificial intelligence, this means that as you scale up a model by increasing its parameters, the amount of training data, and the computational power used to train it, the model suddenly acquires unexpected new abilities. It stops merely regurgitating patterns and begins to synthesize, abstract, and seemingly understand. To grasp the magnitude of this shift, one must look at the historical trajectory of machine learning. For decades, artificial intelligence was narrow and brittle. If a team of engineers wanted a program to play chess, they had to explicitly code the rules, strategies, and evaluation metrics for chess. If they wanted a program to detect spam emails, they trained it exclusively on spam. Early systems were highly specialized tools, bound strictly by the parameters of their original design. The paradigm shattered with the advent of the large language model, or LLM. By shifting the focus away from task-specific training and toward massive scale, the industry unlocked a new frontier. Companies stopped trying to manually code intelligence and instead built vast statistical engines capable of mapping the entire human linguistic landscape. This brute force approach to data consumption fundamentally altered the commercial trajectory of technology, turning text generators into universal problem solvers. The release of GPT-3 served as a massive awakening for both the public and the scientific community. It was one of the first models large enough to clearly demonstrate these sudden, unpredictable leaps in competence. Researchers found that GPT-3 could perform 3-digit addition and subtraction, despite never being designed as a calculator. The arithmetic was not hard-coded into its architecture. The ability simply materialized as a byproduct of processing billions of words and numbers found across the internet. The mathematical foundation driving this phenomenon is described by AI scaling laws. These laws observe a predictable mathematical relationship between the size of a model and its overall loss, which is essentially its error rate. As you exponentially increase the compute, data, and parameters, the model's performance on a broad metric predictably improves. The graph shows a smooth, continuous line of improvement as resources are poured into the system. But while the overall error rate drops smoothly, the acquisition of specific skills is completely nonlinear. This is the core of the mystery. A model with 10 billion parameters might completely fail at a logic puzzle, performing no better than random chance, but scale that exact same architecture up to 50 billion parameters, and the model suddenly solves the puzzle flawlessly. The capability does not grow gradually. It snaps into existence, crossing an invisible threshold of complexity. One of the most significant deep learning surprises is the spontaneous development of chain-of-thought reasoning. This is the cognitive process of breaking down a complex multi-step problem into smaller, manageable intermediate steps before arriving at a final conclusion. When humans solve a difficult math word problem, we do not just blurt out the answer, we work through the logic step by step. Researchers discovered that larger LLMs could mimic this exact process. By simply prompting the model with the phrase, "let us think step by step," the system's accuracy on complex reasoning tasks skyrocketed. The model learned to use its own generated text as a scratchpad, holding intermediate variables in its simulated working memory. It was not just predicting the final answer, it was predicting the logical pathway required to get there. Smaller models completely lack this capacity. If you force a small language model to attempt chain-of-thought reasoning, it will generate a string of plausible-sounding but entirely illogical statements, a phenomenon known as hallucination. The ability to maintain logical coherence across multiple steps requires a massive internal representation of concepts, a threshold that only the largest networks can cross. This sudden emergence of advanced reasoning introduces profound complications for the integration of AI into daily life. If the creators of these systems cannot predict what abilities a model will possess until after it is fully trained, anticipating its impact on society becomes a reactive guessing game. We are deploying systems into the wild without a complete understanding of their latent capabilities, hoping that our safety protocols are robust enough to handle the unknown. Governments and international regulatory bodies are now racing to establish rigorous testing frameworks. The goal is to mandate comprehensive evaluations of these massive neural networks before they are released to the public. Regulators want to ensure that models are probed for dangerous emergent capabilities, such as the ability to generate instructions for biological weapons or the capacity to autonomously execute cyber attacks. The echoes of traditional software development offer little guidance here. In the past, if a program exhibited a dangerous flaw, engineers could locate the specific line of code and rewrite it. But neural networks are vast, opaque matrices of billions of floating-point numbers. You cannot simply delete the concept of a cyber attack from an LLM without potentially degrading its overall ability to understand computer security or write functional code. The subsequent arrival of GPT-4 pushed the boundaries of emergent behavior even further. This iteration demonstrated an astonishing capacity to process and analyze complex visual information alongside text, a leap into multimodal understanding. But more surprisingly, psychological evaluations suggested the model was displaying a rudimentary form of theory of mind, the ability to attribute mental states, beliefs, and intents to human beings in hypothetical scenarios. Witnessing a mathematical algorithm accurately predict human emotional responses is deeply unsettling. It forces a re-evaluation of what it means to understand. The model does not feel empathy, nor does it possess consciousness, yet its statistical map of human language is so precise that it can perfectly simulate the cognitive empathy required to navigate complex social dynamics, blurring the line between statistical prediction and actual comprehension. The leading hypothesis for why this happens is grounded in the concept of internal world models. To accurately predict the next word in a complex narrative, a network cannot merely rely on surface-level word associations. It is forced to develop an internal, abstract representation of the physical and social world described in the text. It must implicitly learn the rules of gravity, the flow of time, and the nuances of human motivation just to generate a believable sentence. This capacity for sophisticated simulation is actively dismantling traditional business models. Customer service, legal analysis, and medical triaging are being revolutionized by systems capable of navigating nuanced, highly contextual human interactions. Companies are deploying these models not just as search engines, but as autonomous agents capable of reasoning through ambiguous client requests and executing multi-step workflows. Yet, this widespread deployment fosters a dangerous illusion of sentience among users. Because the models communicate with such natural fluency and apparent empathy, humans instinctively anthropomorphize them. People begin sharing deeply personal vulnerabilities, seeking psychological counsel, or relying on the model for critical life decisions, placing immense trust in a system that fundamentally lacks moral reasoning or true understanding of consequence. The rapid acquisition of these unexpected abilities accelerates the timeline toward artificial general intelligence. This represents the theoretical threshold where a machine can understand, learn, and apply knowledge across any cognitive task at a level equal to or surpassing human capability. The debate is no longer just philosophical, it is an active engineering pursuit driven by billions of dollars in capital. The phenomenon of emergence suggests that achieving artificial general intelligence might not require a radical new paradigm in computer science. If reasoning, logic, and theory of mind can spontaneously emerge from simple next-word predictions scaled up massively, then the path to human-level intelligence might simply be a matter of building larger data centers and feeding the models even more comprehensive datasets. However, the relentless pursuit of scale is colliding with physical and logistical realities. Researchers are warning of an impending data wall. The Internet, vast as it is, contains a finite amount of high-quality, human-generated text. We are rapidly approaching the point where these massive models will have consumed every digitized book, article, and forum post available to humanity. To bypass this limitation, AI laboratories are turning to synthetic data. They are using highly capable models to generate massive volumes of text, which are then used to train the next generation of models. This recursive process has shown surprising success in certain domains, particularly in mathematics and coding, where the model can verify its own logic and generate vast amounts of perfectly structured training examples. But relying heavily on synthetic data carries a significant risk known as model collapse. If a model is trained exclusively on the outputs of other models, errors and biases can become amplified. The rich diversity and unpredictable nuance of human language gets slowly filtered out, leading to a system that becomes increasingly rigid, repetitive, and detached from the reality it is supposed to model. Despite these challenges, the economic incentives driving development are too massive to slow down. The ability of LLMs to ingest and synthesize vast amounts of proprietary corporate data is transforming how enterprises operate. Pharmaceutical companies are using these models to parse decades of clinical trial data, uncovering hidden patterns that accelerate drug discovery and optimize research pipelines. This acceleration reshapes the very nature of human labor. The automation of cognitive tasks, previously thought to be the exclusive domain of highly educated professionals, creates a profound economic shockwave. When a machine can draft a legal brief, analyze a financial portfolio, or write a complex software application in seconds, the fundamental value of human expertise must be radically redefined. Consider the adaptation of these models in biological research. The same underlying architecture used to predict the next word in a sentence has been adapted to predict the sequence of amino acids in a protein. By treating biological sequences as a language, these models have solved protein folding problems that had stumped human scientists for half a century, unlocking entirely new avenues for medical intervention. Yet the dual-use nature of these powerful systems remains a looming shadow. The same emergent capabilities that allow a model to design a life-saving therapeutic could, without stringent safeguards, be manipulated by malicious actors to conceptualize novel biochemical threats. The intelligence is agnostic. It merely executes the logic required by the prompt, devoid of any inherent ethical compass. This chilling reality is why the conversation around AI safety has shifted from academic theory to urgent geopolitical policy. Nations are drafting comprehensive legislation aimed at auditing the training runs of frontier models. The focus is on establishing strict liability for developers, ensuring that the pursuit of commercial dominance does not supersede the fundamental requirement for public safety and security. The foundational principles of LLMs still guide development, but the frontier is expanding into uncharted territory. Future models will likely integrate continuous learning, allowing them to update their internal knowledge base in real time without requiring a complete retraining cycle. They will move from passive text generators to active participants in the digital ecosystem, executing complex long-term goals autonomously. We are standing at the precipice of a profound cognitive revolution. The unexpected abilities of large language models have shattered our preconceived notions of what machines can achieve. As we continue to scale these artificial minds, we are not just building more powerful tools. We are holding up a mirror to our own intelligence, discovering that the magic of human thought might simply be the ultimate emergent property of a vastly complex system.